Neutron stars and supernova. When a massive star reaches the end of its life, it can end in one of the most violent and spectacular events in the universe, a supernova. This explosion not only marks the death of a star, but also the birth of one of the densest known objects in the cosmos, the neutron star. Understanding neutron stars and supernova gives astronomers profound insight into the life cycles of stars, the creation of heavy elements, and the nature of matter under extreme conditions. A star spends most of its lifetime fusing hydrogen into helium in its core, releasing enormous amounts of energy that counteract the inward pull of gravity. However, when the hydrogen fuel runs out, the core contracts and heats up, allowing heavier elements, such as carbon, oxygen, and silicon, to fuse. This process continues until iron is formed. Unlike lighter elements, iron does not release energy when it fuses, and so fusion in the core stops. Without the outward pressure generated by fusion, gravity takes over. The star's core collapses rapidly, and the outer layers fall inward with tremendous speed. The infalling material rebounds off the dense core, producing a titanic explosion known as a supernova. During this collapse, the core's protons and electrons are forced together under immense pressure, forming neutrons and releasing neutrinos. The result is a compact sphere composed almost entirely of neutrons, known as a neutron star. Despite containing up to twice the mass of the Sun, a neutron star is only about 20 kilometers across. To imagine its density, 1 teaspoon of neutron star material would weigh around 1 billion tons on Earth.
Some neutron stars rotate extremely rapidly, sometimes hundreds of times per second. These spinning neutron stars emit beams of radiation from their magnetic poles. If these beams sweep across Earth, we detect them as regular pulses of radio waves or light, and we call such stars pulsars. The first pulsar was discovered in 1967, and since then, thousands have been found, each acting as a cosmic lighthouse, marking the presence of a neutron star in space. Not all massive stars become neutron stars. If the collapsing core is more massive than about 3 times the Sun's mass, even neutron degeneracy pressure cannot stop the collapse, and the star continues to compress into a singularity, a black hole. However, for stars of moderate mass, the collapse halts at the neutron star stage, leaving behind a small but incredibly dense remnant surrounded by the expanding debris of the supernova. Supernovae are among the most important processes in cosmic evolution. They scatter the elements produced inside stars, oxygen, carbon, silicon, iron, and many others, into interstellar space. These materials later become part of new stars, planets, and even living organisms. Every atom of iron in human blood, for example, was forged in the heart of a star and scattered into space by a supernova long before the Sun and Earth were formed. In this way, supernovae are not only the end of stars, but also the beginning of new worlds. There are different types of supernovae depending on how the explosion occurs. The most common are core collapse supernovae, which mark the deaths of massive stars, and thermonuclear supernovae, which occur when a white dwarf star in a binary system gains too much mass from its companion and undergoes a runaway nuclear reaction. Both types release enormous energy, outshining entire galaxies for weeks or months. The light and particles from supernovae can travel for thousands of years before reaching Earth. Astronomers have recorded several supernovae visible to the naked eye throughout history. One of the most famous occurred in 1054 CE and was recorded by Chinese astronomers. The remnant of that explosion is the Crab Nebula, which still glows brightly in the sky today. With a rapidly spinning neutron star, a pulsar at its center. Modern telescopes and observatories allow scientists to study supernovae and neutron stars across the electromagnetic spectrum, from radio waves to gamma rays. Space-based observatories like the Chandra X-ray Observatory and the Hubble Space Telescope have captured detailed images of supernova remnants, revealing the turbulent structures created as shock waves expand into space. Observations of pulsars also help physicists test the laws of nature under extreme conditions. For example, by studying the timing of pulsar signals, scientists have confirmed predictions from Einstein's theory of general relativity with extraordinary precision. Neutron stars can also exist in binary systems, orbiting another neutron star or a normal star. When two neutron stars spiral toward each other, they emit gravitational waves, ripples in the fabric of spacetime, predicted by Einstein and first directly detected in 2015. In 2017, the collision of two neutron stars was observed both through gravitational waves and electromagnetic radiation, marking a new era of multi-messenger astronomy. The collision produced heavy elements like gold and platinum, confirming that such cosmic mergers are one of the main sources of these rare materials in the universe.
The study of neutron stars in supernovae is therefore at the heart of modern astrophysics. It connects the smallest scales of particle physics with the largest structures in the universe. It reveals how matter behaves at densities far beyond anything found on Earth, how stars live and die, and how the universe renews itself through cycles of destruction and creation. These extraordinary objects remind us that the cosmos is both violent and creative, that the death of a star can give birth to the elements of life itself. In the end, neutron stars and supernovae are cosmic symbols of transformation. They show that even in the universe's most catastrophic events, there is beauty, order, and renewal. The remnants of long-dead stars continue to shine, pulse, and send their energy across space, telling us stories of creation, destruction, and rebirth that stretch across billions of years. Studying them is not only a pursuit of scientific understanding, but also a reminder of our deep connection to the stars, for the atoms that make up our bodies were once part of such magnificent explosions.